Welcome to the second lecture in the series of biochemical engineering. We will start off today from where we left, and as the title of the lecture suggests, this is going to be concentrated towards kinetics of enzymatic reactions. So we'll just a quick wrap up from where we left in the last class. So the enzyme essentially, as I said, is a catalyst which doesn't participate in the reaction but accelerates the reaction by reducing the threshold activation energy. So if we are to denote the reaction of S being the substrate going to P by a reversible reaction, S reversible going to P, then in the presence of the enzyme it turns out that E plus S goes to P plus E, where E is the enzyme that reacts with the substrate to generate the product P, and the enzyme is regenerated back. Okay. So this is the basics of the kinetics. But now what we're going to do in today's class is delve a little deeper into the kinetics and try and understand how this really happens, how the enzyme catalyzes or accelerates the reaction and things like that. And as I said, the 2 points here to note is that the enzyme is not consumed in the reaction, a very important point to note actually. It only accelerates the reaction, and it does not alter the final equilibrium state. So both of these are important points which will come into play while we do our calculations. Today I would like you to have your exercise books and pens ready, because we're going to do some small calculations as we go along. So just a quick wrap up, from yesterday, the RS, the reaction rate for the Michealis-Menten kinetics, which is the most popular kinetics used in all of biochemical engineering, and much of this course that we are going to do is going to be concentrated towards Michealis-Menten kinetics, is given by, the reaction rate is given by R max, which is a constant and the maximum reaction rate possible, times Cs divided over Km plus Cs. Now, Cs being the concentration of the substrate, Km is called the Michaelis constant, and its value is evaluated by finding out what is the the Cs at which Rs goes to half of R max, right? So let's go a little beyond this, and let's try and understand how this reaction kinetics comes out of the reaction between the enzyme and the substrate, right? So we cannot accept this reaction as it has been given to us. So what we'll do today is a derivation of the Michealis-Menten kinetics, and I would like you to participate in that, as I said, by going through the derivations with me while we go through this lecture. So the first step so if I am to ask you to split up the last reaction that we have, which is E plus S going to P plus E, intuitively, so there'll be, let's think of it as a two-step process. Okay, so the first step in this process is going to be the enzyme E reacts with the substrate S to form a complex ES. Okay, so I want you to write down in your copies very quickly what that reaction is going to be. So very straightforward thing, just that the enzyme E reacts with the substrate to form the complex ES. Because if you remember, when we did the thermodynamics of it, here in the presence of the enzyme, a complex is formed, which is AEB plus. So here we are not dealing with two substrates. This diagram is for two substrate A plus B, but now we are dealing with only single substrate. So as a result of which, what will happen is S is going to react with the enzyme to form a complex SE, right, which will then go to the product. This has to be clear. So this is the mechanism of the Michealis-Menten kinetics, right, that you first form a complex, the enzyme first reacts with the substrate to form a complex, and then from that complex you get to the product, right. So now let's get our pen down to the paper and try and write this reaction. Done? Okay. So this is the reaction as it turns out. So which is that E, the enzyme, reacts with the substrate reversibly excuse me, reversibly to form the complex ES. Okay, and the forward rate constant here I've put as K1, and the backward rate constant I've put as K minus 1. Important to note, what is given in parenthesis is that this complex ES that is formed is an unstable complex that is short-lived. It doesn't live for a very long time. It degenerates or degrades or changes over to something else, and So the next step, and this is an intermediate species, right? So the next step is this. In this second step, this unstable complex, that is ES, which is a short-lived complex, dissociates to form the enzyme and the product. So write that reaction down. Right? So what is it, Sahil?
ES gets P plus E.
What kind? Reversible or?
Reversible.
Huh?
Reversible.
So all of you wrote reversible? Okay. Actually, it's irreversible. As I said that in the last class, that yeah, all reactions are, you know, typically reversible. But in this reaction, you have to have it irreversible. Otherwise, not enough product are going to be formed. And if you look at the overall reaction is actually reversible. Okay. So it's obvious that this reaction also has to be reversible, but we take it as a reversible reaction because the backward reaction is very slow typically, and this, it turns out, is a rate limiting step, right? I hope all of you are aware of the concept of rate limiting step, which is that if you have multiple reactions, the rate, a network of reactions, then the rate of the final reaction product formation is governed or dictated by the rate of the slowest step, right? So I give this example in class, you know, that for example, if you are walking somewhere with your little sister and she walks much slower than you, then the speed at which you can walk is governed or dictated at the speed at which she can walk and not the speed at which you can walk. So you know, this kind of examples will probably imprint this concept of rate limiting step, and this is a very important concept in all of chemical engineering. So whenever you have a network of reactions, you have to go down and figure out what is the rate limiting step, and in this case this is the rate limiting step. Why are we so worried about what is the rate limiting step? Because the rate of formation of product is going to be dependent on the rate limiting step. Okay, so this is the rate of disappearance of the substrate. Okay, so if you look at reaction 2 over here, the substrate disappears in reaction 2 from the reversible reaction, right? Is it clear? So these are the two terms that come in from equation 2. Look at equation 2. There is a forward and a backward reaction, and all I have written in equation 4 is simply the rate of, so the disappearance of the product, so dCs dt is the rate of disappearance due to the forward reaction minus the rate of disappearance due to the forward reaction plus the rate of formation due to the backward reaction. Fine. Okay. Now, can you write what would be the rate of product formation? Product is here, and product is formed from equation 3. Right. So it should be very straightforward. What is that? Yeah. We'll come to that a little bit. So what I now want you to look at is, this is the intermediate species, right, which is unstable and short-lived. Okay. What I now want to look at is what is the balance for this intermediate species. Like we wrote a balance for the substrate, we can write a balance for the product, which you already have written. What is the balance for the intermediate species? And I want you to write that down. This is very straightforward because the intermediate species is part of two reactions, one of them reversible, one of them irreversible. So there will be just an additional term there. So just use equation 2 and 3 to write what is your dCES dt. Fine. So this is, I hope, what you got, right? One for the forward reaction, one for the backward reaction of equation 2, and one for the reversible reaction of equation 3. So I want to go back a little to this. Now, one of the important things in all of this biochemistry and biochemical engineering is the fact that there are some constraints on the system. What are these constraints? It is a mass balance constraint, or in other words, when you're talking of an enzyme, these enzymes, as you know, participate in the reaction, do not participate in the reaction, overall reaction, participate in the intermediate steps of the reaction, but not in the overall reaction. So at the end of the day, the amount of enzymes remain unaltered, and this is a very important thing physiologically. Why is that? Because these enzymes are typically available in trace quantities in the human body. Okay, so you cannot afford to waste them. So one of these physical constraints boil down or give rise to what is a mathematical constraint on the amount of enzyme that is present in the system. And if you look at this, and we have done this before, I know, if you look at this, what is the amount of enzyme that is present in the system? What are the different forms in which the enzyme is present?
Free E and combined state ES.
Absolutely. So the free enzyme and in the enzyme in the complex form. So if you look at this, so look at equation 6. Okay, CEO or CE0 is the total amount of enzyme present before the reaction starts. That equals the amount of free enzyme and the enzyme in complex form. I'm sorry, in here I wrote it in the other way, so I should have written CE0 equals CE plus CES, right? Because here free enzyme comes first. So the free enzyme plus, so which is CE, and the enzyme in the complex form, which is CES, right? So this is my equation, and I want you to make a note of that. This is known as a constraint equation. So whenever, this is a very simple system that we are trying to derive, and we will try and derive much more complex systems later on in this course, and in the and the assignments and tests will probably give you a lot more complicated systems to solve. One of the things that is important and to make note of and always remember and put it into practice is the fact that you have a constraint equation. So these systems are biological, all biological systems are governed or are dictated by certain constraints, and to figure out what that constraint is. Okay, so this is known as a constraint equation. So the rate of product formation is something that you have already written. Okay, now I give you a few minutes, couple of minutes. What to do is that this rate of product formation is written in terms of CES, the complex, right? The concentration of the complex. What is the problem with the concentration of the complex? It is an unstable compound, as I said, intermediate unstable compound, and it is not measurable. Okay, value of that is not measurable. So what we have to do is we have to calculate the value of this concentration intermediates of the intermediate species in terms of parameters and variables that we can measure, right? And then we have to put it back into the rate of product formation to be able to get what the final rate of product formation is, right? So this is what I want you to do quickly in the next couple of minutes, is calculate what is CES. Okay. So to help you, I will just give you some hint. So what do you think, Pallavi, would be the first thing that you need to do here?
So we'll be using the constraint equation.
Constraint comes later. Before that, what is the yeah?
So the ultimate is very short-lived.
So yeah, right.
So the dCs by dt equation which we have
Is going to be,
we can take to 0.
that is going to be 0. So this is very good. So that's the key assumption that we have to use. So look at equation number 8 I put up there. So the quasi-state, this is known as the quasi-steady state assumption. That is, a complex is very short-lived, it breaks down very quickly, and as a result its rate of accumulation is 0. So d dt of CES is 0. So what you need to do is look at equation 5 where I gave you the rate of formation of d dt of CES, right? Put that equation to 0. Okay, so that is what you need to do, and then use the constraint. So couple these two to now write CES, express CES. It's very straightforward. Express CES in terms of the other variables. So from equation 5 you will get CES equals K1 over K minus 1 plus K2 CS CE, right? Right. So I have it on the screen now, that the ddt, once you put the ddt of CES equals 0, you get CES equals K1 CS, so times CE over K minus 1 plus K2. Clear? Lisa? Clear? Okay. Okay. Now what you need to do is use equation 9, which is the equation I got here, on the constraint equation over here. Okay, because you have now got CES. So, what you need to do is substitute CES over there. You see, Arush? So, equation 9 I got over here, substitute it back to equation 6. And then you can express your CE as a function of CE naught and CS. Why are you trying to do this, Krishna Prasad? Why are we trying to express CE as function of CE naught and CS?
So that we can replace CS in the.
I know why.
So that we can define the rate of reaction.
I know, but why not keep CE there?
CE is not. We don't know CE.
CE is an evolving quantity. We are not aware of what CE is. Okay, we are aware of CS because CS is something we can measure at any. CS is also dynamic quantity, remember, but CS is something we can measure at any point of time. CE naught is a known quantity because it is something that we started with. So, we want to express everything, all our parameters and values in terms of CE naught and CS. Okay. You got it? What do you got? You got the same as what I have on the board? Equation 10. Okay. And then CES now is given by, so once you got CE as a function of CE naught and CS, then you can simply replace that in the CES equation and you get a slightly more complicated relation, but you get CES as K1 CS CE naught K minus 1 plus K2 plus K1 CS. Okay, fine. What else shall we do now? What is the next step?
CES is to fund reaction, rate of reaction.
Which one? Which reaction?
dCq/dt equals to K2 into CES.
Very good. Yeah. So, what we need to do now is figure out what is the rate of product formation, rate of reaction, so to say. So, the rate of substrate, this is the rate of substrate, the rate at which the substrate is taken up, and actually you will see that this is equal to the rate of product formation. Why is that, Ashwin? Yeah, no, that's not the final answer. I mean, that's an easy answer, but I am evaluating. The question is, I am evaluating the rate of substrate production formation, right? But what do I actually want to evaluate? I want to evaluate the rate of product formation. But I said the rate of substrate that is taken up consumption equals to the rate of product formation, and intuitively it's very clear, right? Because S going to P, so how much is equimolar thing? So if X amount of S is taken up, X amount of P is going to form. Intuitively it makes complete sense, but what I am trying to ask you is, mathematically, can you prove that to me? This is there right in front of your eyes. You just have to tell me which equation to use.
It's overall reaction.
No. What is that? Which equation do you use to get that?
E plus S equals to P plus.
No, it's very straightforward. Equation 5 and equation 8. Equation 5 is this. Okay, the ddt of CS equals that you put equal to 0, then you will find that the rate of product formation equals to the rate of substrate consumption, right? Okay. So, essentially what I am trying to say here is that in this slide is that if you look at RS is dCs dt, which equals minus of dCp dt, fine. So, I want to go through this, want you to go through this calculation quickly. You can do it this way, or there is another easy way, is Kc ddt of Cp equals K2 times CES, right? So, you simply need to multiply this by K2. Clear, Pallavi? Everybody, Lisa, are you with me? Okay. We simply multiply this by K2, then you will get the del T of Cp equals this, fine, and this is what we get here. K2, simply multiply this same thing multiplied by K2. That is my the rate of product formation equals to the negative of the rate of substrate consumption. Fine, good. So, now the question is, so this is what we got. Say this is the rate of product formation, or this is the rate of substrate consumption. This is what we got. Now my question is that how do we recast it into the Michealis-Menten form? Because what we started with, see, these are two objectives. We said first that it's a Michealis-Menten form. It has been told to us that it's a Michealis-Menten form, but we do not accept that as scientists, as something God-given. So we started off with the very basics and started to derive that. So there is no assumption or inbuilt assumption that it's a Michealis-Menten form at any point of time. After we have got this rate expression given by equation 12, what we are trying to figure out is this a Michealis-Menten form? So what do we do to do that? What we do is the Michealis-Menten form was given to us here, equation 1, and what we need to do is we need to compare this form with that form and figure out that how can we recast this form to that form. So equation 12 that I got, how can I recast my equation 12 into a form that looks like the Michealis-Menten form? So what do I need to do? So this is a Michealis-Menten form. I need to compare this with what I got. Clear? So if when we compare this, it's very straightforward. What turns out is, can you see what turns out? What turns out is R max equals K2 CE naught, and Km, which is known as the Michaelis constant, is K minus 1 plus K2 over K1, and R max is the maximum rate. Okay. Who will tell me? Will you tell me, Krishna Pratap, why R max is intuitively why R max is K2 CE naught?
It is a maximum rate that will be possible.
Yeah, why is that?
If all the enzyme
Right. If all the enzyme had reacted and formed the product, then the CE naught, so if there is no free enzyme left, then CE naught is the total amount of enzyme that would be in the complex form, and CE naught is the total catalyst. So there will be no free enzyme left, in which case my R max is the maximum. So the maximum reaction rate possible. This is something that you need to understand intuitively, that because despite all the reactions and the equations we write, there might be times when you might have to just figure out in a problem that what is the maximum reaction rate intuitively. So what I'm trying to promote is not just a mathematical way of looking at it, but sometimes an intuitive way of looking at it as well. So R max is K2 times had the total amount of enzyme reacted. Okay, so that's the maximum possibility. Clear? And Km just comes out of the calculations, right? Is it physical understanding clear to all of you? Okay. So we'll move on now. What we'll do is how to evaluate these constants. Okay. So these are the two R max and Km are now my two constants. What have I been able to achieve through this by recasting it in the Michealis-Menten form? Can you tell me that? Why did I say once I recast it into the Michealis-Menten form? I had no reason actually. Michealis-Menten derived the form, good for them, but I don't have to necessarily recast my equations in that form. Why would I be motivated to do that? What do I gain by doing that?
We only have two variables.
Very good.
We can calculate that way.
Very good. Not variables, constants, parameters. Yeah, very good. So, so what we can manage to do or manage to achieve by recasting it in the Michealis-Menten form, you see in this first form you have 1, 2, 3, 4 variables, so 4 parameters: C naught, K minus 1, K2, and K plus 1. Okay. When you recast it in the Michealis-Menten form, you end up with just 2 parameters. Why is that good for us? Because we have to finally, at the end of the day, evaluate these parameters experimentally, right? So once we recast it in the Michealis-Menten form, it's much easier to evaluate 2 parameters experimentally than 4. And some of you, if you're doing experiments, you know how hard it is to, Arush, you probably know how hard it is to evaluate these kinetic constants experimentally. So if you reduce the number of kinetic constants as much as possible, it just makes your day easier, right? So what we'll look at now in the next few minutes is how to evaluate these kinetic constants. So what do you think, give me a sense. This is your rate equation, for example, the Michealis-Menten. What do you think would be an easy way to measure these constants?
Experimentally, you can do, if we perform experiment at a very low concentration of CS.
Mm-hmm.
Again, if you perform an experiment at a very high concentration of CS.
Mm-hmm.
So we have two rates.
Right, that's one way. Yeah, that's a very good way actually. But that's a clever way actually of doing it. But one of the things you can do simply is measure the rates at various concentrations. Okay, straightforward way. This is not a first order reaction, but I'll show you how to convert it to something similar to that. So very straightforward way would be to just measure these rates at various concentrations, and what happens is once you measure these rates at various concentrations, you get a plot like this. So these numbers that you see here are actually numbers corresponding to certain experiments, and RS is a rate versus CS, the concentration, and this is in micromolar, the concentration in the x-axis, and the rate in the y-axis is micromolar per second. Okay, so what happens is that what is said, the RS is R max CS over Km plus CS. You plot the whole thing, okay, because it's not a good idea to do what you're talking about is known as asymptotic analysis. What you have on the left, if you see on the left, case 1 and case 2, these are known as asymptotic analysis, and I think I mentioned this yesterday in class, that asymptotic analysis is very important in all kinds of engineering analysis you do, because you need to figure out what is the maximum, what is the minimum, and then your final solution is bounded by these two, right. So if you look at the plot over here, this is asymptotic solution. So case 1 is case 2, let's look at, which CS is very small. Okay, CS is much trace quantities of CS you give, and the RS that you get, the reaction rate, is R max CS over Km. Okay, I explained this yesterday, but I'll show it one more time today. So if CS is very small, then this term in here is not present. Okay, negligible as compared to Km, and you get R max CS over Km. If CS is very large, then Km is negligible over here, and CS in the numerator and denominator cancel out, and you get simply RS equals R max over Km. Right? Rx equals R max here, right? So if you plot this, this is what you get in the two asymptotic cases. One is turns out to be the 0th order case, this one, and this is the 0th order case on the top, and one is the first order case, which is near for small concentrations of CS. Now what do you do for small concentrations? You know the slope, so you measure the slope, and the slope you know is R max over Km. For large concentrations, you know that the slope is R max. Okay, RS is R max, and so straight away you can evaluate your R max from the asymptote, the saturation limit it reaches, excuse me, and once R max is evaluated, then you can use your slope to evaluate your 1 over Km. Okay, fine. This looks good and easy. Now I'm going to quiz you a little bit here. At large concentrations of CS, small and large concentrations of CS, intuitively, physically tell me, why does a system approach a first order and a 0th order? Let's start with the easy one, which is at large concentrations of CS, why does a system approach a 0th order solution?
Reaction is limited by concentration of catalyst enzyme, concentration of enzyme at large concentration.
Right. So Rmax essentially contains the enzyme concentration, the initial concentration of the enzyme. So the substrate is no longer limiting reactant. Okay, it doesn't matter how much substrate you're putting in, because you are putting in enough amount of substrate. The substrate is no longer a limiting reactant. Okay, so as a result, so the rate is independent of the substrate. Is that clear? Okay, so that's what a 0th order reaction is essentially. You know, these are questions often asked in quizzes, that a 0th order reaction, what does a 0th order reaction essentially mean? Does it mean that the rate doesn't depend on the reaction rate at all? Then it will mean that, you know, it doesn't matter how much substrate I put in, the reaction rate is still the same, right? What would a 0th order reaction mean, Lisa? Like, if it might mean that if there is no dependence on concentration, if I put a large amount of substrate and a small amount of substrate, it makes no difference, right? Is that so? In a 0th order reaction, if the rate is independent of concentration, does it mean that it's a material how much material I put in?
So it depends on the initial concentration.
No.
Depending on the concentration, the reaction order will change.
No. If I'm saying the reaction order is first order itself, so the 0th order itself, does it mean that it's independent of the amount of substrate that I put in? It means it's independent, but can I put in a very small amount of substrate? No. That is the point. That is what I want you to realize. It's independent, but at a large asymptotic value of the substrate. So what does the whole concept of zeroth order reaction mean? That you are giving enough substrate for the system to be independent of the concentration. There are very few systems in the universe, in reaction engineering universe, where the system is actually independent of concentration. Okay. So if the zeroth order reaction mean that it's independent of concentration? No, not really. It looks as if it's independent of concentration, but it's not really independent of concentration. What it means is that for a large amount of substrate being present there, okay, the system behaves as if it's independent of concentration. Now you decrease the substrate concentration, you will figure out that it starts to be dependent on concentration, and that is what happens at the small concentration. What you find, it linearly depends on concentration, which means that it's limited actually by the amount of substrate that you put in. Okay, so this is a physical, it's very easy to and good to do the mathematics, but at all points of time we should have the physics of what's really happening at the back of our mind. So we will go on from here. Is this clear to you? So this is how we evaluate. You evaluate the Rmax from the top asymptote and the Km over the bottom from the bottom asymptote and figure it out. That's one way of doing asymptotic analysis. Can you tell me what other ways could be there apart from asymptotic analysis if I want to use the whole range? Here I am not using the whole range.
Plot 1 by R versus 1 by C.
Very good. So this is known as a Lineweaver-Burk equation. Okay. So what you do is, look at this. So what you do is, you had Rs given by that formula that we had here. Here. So if you take the inverse of this, okay, just take the inverse of this 1 over Rs, then what will happen is 1 over Cs will come in the denominator, and this is what happens. Km over Rmax 1 over Cs plus 1 over Rmax. Now if you look at it, what happens, Lisa, is that 1 over Rmax, 1 over R is, and you plot 1 over Rs against 1 over Cs, okay, then they are linearly related, right? So then you can use the whole range of data. Why do you think, Krishna Pratap, it's sometimes better to use this equation rather than the asymptotic one?
Error is less.
Because in experiments, when you actually use experiments, you're not sure if your data in the two asymptotic limits are necessarily correct, right? Because and those are more prone to errors. When the concentration is very small or the concentration is very large, those are more prone to errors, and you actually want to use your data through the entire over the entire spectrum, which you cannot use if you're just doing an asymptotic analysis. So that is why this is sometimes better, because in this way you can use your data over the entire spectrum. And this is how a plot looks like. This is a representative plot of the system. So if you look at this, so your slope is here, look at equation 12, your slope is here 1 over Rmax, sorry, your intercept is 1 over Rmax and your slope is Km over Rmax. So once you evaluate your intercept, you can directly evaluate your slope from this. Okay, I'll just give you a few seconds to, if you want to make a note, just make a note of this. So 1 over R is linearly related with 1 over Cs. Okay, shall we move on? Okay. So there are a couple of other relations or equations that are used. So I just showed you the Lineweaver-Burk and the asymptotic method, and there are two Scatcherd equation and Scatcherd plot, and the Edey-Hofstee equation on the plot, respective plot. These are also used to obtain these. Why do we go into different forms of these plots? The reason is, when you evaluate these experimentally, the data may be available in different forms at different points of time, depending on what kind of experiments you are doing. So here what you have is Cs over Rs is Km over Rmax, Cs over Rmax in the Scatcherd equation. So if your data is available as Cs over Rs, so maybe your one set of data is available as Cs over Rs versus Cs. Okay, it's possible. It doesn't. We're not aware how you collect the data. So depending on how you collect, so there are these several options that are available to you, and depending on how you collect your data, you actually decide what form of the plot you want to use. So the equation 13 uses Cs over Rs, so you measure Cs over Rs, that's your y-axis, and your x-axis is Cs. The equation 14 uses Rx equals Rmax minus Km Rs over Cs. So this is very straightforward. So your intercept is going to be Rmax, and again you use your Rs instead of Cs over Rs, you just use Rs over Cs. Okay. Now, till this point is very good and wonderful, but the thing is that all our analysis that we have done, we have based it on an assumption, and a very important assumption, which is the quasi steady state assumption, which is that the CES that you have, the intermediate species, it's short lived and accumulation is 0, ddt of CES is 0. That was the assumption we made. Now what we have to do is, as not just work as engineers but as scientists, we have to go back and evaluate that whether that assumption is correct or not. Okay, so what do we do about it? Sahil, any thoughts?
Quantitatively or like
Harush?
Experimentally?
Well, experimentally you can, but
in the intermediate, like in experiments,
We don't have traces. We have traces of this complex.
at different points while conducting the experiment.
yeah, you can use fluorescence and stuff like that. That's a possibility. What we might do is theoretically is that we can actually go and not make that assumption. We made that assumption and did the calculations, and we can actually go and not make that assumption, and then see based on our rate constants whether that assumption is valid or not. That's a possibility. So we can do the same analysis not making that assumption. It makes that calculation a little complex, but we can do that and then compare that with the system where you make that assumption. So that's always, when you validate something, when you validate a model, for example, if you have a lower dimensional model, you use an average model and you want to validate your average model, what is the procedure? What you do is you take the full 3-dimensional model, compute the solution of that, you take the average model, compute the solution of that, and compare the average solution with the full solution, and if that error between the two is not high, there is obviously going to be an error, because once you make an assumption, there is always going to be an error. But if the error between these two is not very high, then you say that your assumption is more or less correct. So that is what we are going to do. So this is an assumption that we made, that the complex formation, that is a fast step, and it, as a result, the quasi steady state is unstable and there is no accumulation. And this was the equation that was related to that. Now if I ask you to, we actually wrote that equation, so these are the equations. So if I ask you to go back to that, I think equation 5 or something, if I remember, just give me a minute. Yeah, equation 5. So this is where we put the assumption in. This I equated to 0. If I do not equate this to 0 and I want to solve this in conjunction with others, okay, we can do that. One of the assumptions that we make while solving, and that is exactly what we are going to do. We are going to solve equation 5. Is it clear? We are going to solve equation 5, making some small assumptions, but not make the big assumption that its accumulation is 0. Okay. Yeah. So the assumption that we make is Cs at this period is equals Cs naught. Okay, that's the only assumption we make. What does it mean? That it's at the initial stage of reaction. As a result, the total amount of substrate that is formed, that is present, equals the total amount of substrate that was initially present. That's a small assumption that we make, and once we make that assumption, we can go ahead and solve this. Okay. So this is my balance equation, right? And all I am doing over here, so how is it different from equation 15, is that all I am doing over here is I am substituting Cs by Cs naught, right? Okay. So who will tell me how to solve this equation? The method. I am not asking for the solution, but what would be the method? It's very straightforward, right? There's no method involved. It's dy dt equals some constant minus a minus by, right? So you can go ahead and solve it. It will be exponential solution. So this is what you get once we solve it. What is the assumption at t equals, so what is the initial condition at t equals 0? There is no substrate, no complex that is there. Fine. So you can write down equation 18, which is the solution of the system. Okay. So it's an exponential solution, equation 18. Now from here you have to come up with an idea that, so the solution is good, but you have to come up with an idea what to do with it. Where do we go from here?
So we can have a plot of time with C's and
our assumption will only validate this K1 into Km plus C naught Cs naught is very very large. This part
What does anybody else, what do you think? So this is a first order reaction, right? And so when you do a first order reaction, what is important is the time scale for reaction. What are you trying to measure? How fast the reaction is, you know, what you said, right? You're trying to measure how fast the reaction is. So how do you evaluate the time scale for reaction?
time constant.
Yeah, the time constant, not the time constant, but the inverse of the time constant, right? Okay. So if your time, the constant which is a prefactor of t is something, it's the inverse of it, essentially the time constant. Now, so what will you do from here? What you have to figure out what the time scale for this reaction is, right? Or in other words, what is the effective rate constant for this reaction is. And if you look at it, what he said, just now Krishna Pratap said, that's very correct, that if you look at this equation 18, what is the term that matters when it comes to the dynamics? See, we are trying to understand the fastness of the process, okay? How fast this process is. If it is fast enough, then our assumption is pretty good. We are good with it. So we are trying to evaluate the fastness of the process. What is the part or the term that has to do with the fastness of the process? The term within the exponential, right? Because that is the one that has the time in it. So we have to take that prefactor of time out, and we have to compare it with the time constant for the other reaction. Okay, so if you look at this, this is the rate constant for the first step. Okay, K1. Let me go back. So K1, yeah, this one K1 Km plus Cs naught. This is my rate constant for the first step. Now the second step is, I'll go back again. This equation 3, okay, Es giving E plus P. So that is again a first order reaction with respect to Es, and you can evaluate its rate constant. Clear? So what we have to do is we have to compare the rate constant or time constant or rate constant, whatever the time scale of equation 2 or reaction 2 with the time scale for equation 3. Or in other words, what it means is that equation 2 has to be much faster than equation 3. If I am talking in terms of reaction time scales, how does it translate? The reaction time scale for 2 is very less as compared to reaction time scale of equation 3. Is that clear? Reaction 2 has to be much faster than reaction 3, which means that the time scale for reaction 2 has to be much smaller than that of reaction 3. Clear? So we calculated our time scale for reaction 1. Now what I wanted to do is calculate the time scale for reaction 2. I can help you with, I can give you reaction 2 here. So that is equation 3. Okay. What is it going to be? No idea. So it's going to be same as what you see on the board, reaction 12, equation 12, with the exception that CS can be changed to CS naught, because that was the initial idea, that we can keep it as CS naught. Okay, because it's a pseudo first order approximation we are making over here. Because when you couple, see, what we are trying to do is we are trying to decouple the phase 1 from phase 2, but in reality they are coupled, right? Unless you evaluate what your ES is, you cannot. So what should you do? Ideally, what should you do here? You have, if I ask you to solve this, okay, we can do that as an assignment. I don't have the time in this class to do it. This is your CES, right? So if you write your next equation, what should it be? Our next equation is ES giving E plus S, E plus P, right? So your CES is given here. You know CES as a dynamic. So write that equation quickly. Write the balance equation here. I have it here. So write the balance equation for the second reaction, formation of P, right? Okay. CS. Now you know CS. Put the value of CS. Is it clear? K2 into CS, and all you have to do is you have your CS over here, and this is your CS. You have to just put the value of CS over here. Okay. So the rate constant for that turns out to be something like this. Okay, and for the second phase, K2 into this part. Now what we are doing here, there is an assumption implicit over here, which is that what is the assumption here? Tell me. K2, if I just multiply this by K2, okay, then you have K2 C into C naught CS naught E naught Km plus CS naught, fine. But when I put the rate constant over here, I am just putting K2 C naught Km plus CS naught, and this part is missing over here. The time part is missing. Why am I? What is the assumption implicit in that? There is obviously an assumption. That's because that's not the right answer. You know that, right? Is it clear? The right answer is you have del Cp del T equals K2 into CES, and CES is given by that. So your del Cp del T is essentially K2 into this part times exponential minus time. So the rate itself is now a function of time. You see the difference. In equation 17, the rate itself is not a function of time. Only after you integrate it, it becomes a function of time. But here in equation 18, not equation 18, when you do the second part, the rate itself becomes a function of time, right? But I am trying to do a pseudo first. So this is not a first order reaction, but I am trying to do a pseudo first order approximation of that. Okay, and as a result, I convert this into first order and say that the reaction rate is simply K2 CE naught Km plus CS naught. Is it clear? Let me go through one more time. So this is my CES, right? CS naught E naught CE naught over Km plus CS naught times this. Okay. Now when I write like this, this is what I get, K2 CES. You can change it to CS times what I miss over here is this times the exponential part. 1 minus exponential part is there, but I neglect that exponential part. Why? Under what circumstances do I do that? So right, very good. So the assumption, the whole idea or the concept behind that, we are analyzing the first part at initial times, okay, at small times, whereas we are analyzing the second part at large times. And if you look at this, it's a little complicated, so I am giving you a little bit of time with this. So if you look at this, so what happens is exponential minus K1 Km plus CS naught, this part will go to 0, because at large times this part will go to 0. So only the prefactor, the part that you see over here is going to remain, and that is going to be your rate constant, right? Fine, clear to everybody? Ashwin, okay, Lisa, okay. So this is a little complicated, so that's why I wanted to give you enough time for this. So now what we do is what we had discussed, which is that step A has to be much faster than step B, or in other words, two ways of putting it. The rate constant of step A has to be much higher than the rate constant of step B, or the reaction time for step A has to be much smaller than the reaction time for step B. Fine. So, as I put here, the rate constant for step B has to be much smaller than the rate constant of step A, and when you put that over here, you find that the rate constant for step B is something we got here, K2 CE naught over Km plus Cs naught, has to be much smaller than the rate constant for step A, which is K1 times Km plus Cs naught. Okay. Fine. So, what we will do is, so this is, you are done with this. Okay. So, now you essentially have what you have is a relationship between your enzyme concentration and the substrate concentration. You see what is happening. The last equation that you see, essentially see your K1, K minus 1, Km, these are constants for the system. You have no control over these constants, right. What you have control over are the substrate concentration and the initial enzyme concentration. So, in order to make sure that Michealis-Menten kinetics is satisfied, you have to make sure that this relationship between the initial enzyme concentration and the initial substrate concentration is followed, right. Or in other words, let us not say that in order to make sure, and in other words, if the relationship between CE naught and CS naught, this relationship between CE naught and CS naught is maintained, then Michealis-Menten kinetics is valid, otherwise it is not valid. So, let us not decide forever that Michealis-Menten kinetics is always valid, given whether the sun shines or whether it rains. That is not the thing. So, only under certain conditions it is valid, and these are the conditions. What I think some of you might have to go, but what I wanted to do, is there any question on this? Let me address that if there is. Okay. So, what I will quickly go to do is, we just have a couple of minutes more, summarize for you what we did today very quickly, and in the next class we will start with regulation of enzyme activity, and I will give the introduction later, but very quickly I will just summarize for you. So, this is where we started, the Michealis-Menten kinetics, and we said that the Michealis-Menten kinetics is given by R max Cs divided by Km plus Cs, but we do not want to take it at face value and we want to derive it. So, what we did was we said that the enzyme reaction that happens is a two-step reaction. In the first step, the enzyme reacts with the substrate to form an unstable short-lived intermediate ES, which has a short life but reduces the threshold energy barrier, so that the reaction happens and it is accelerated. Fine. In the next step, what we said is that this complex now breaks down to form the enzyme and the product, and this reaction is more or less irreversible, in the sense that even if there is a backward reaction possible, it is very slow as compared to the forward reaction. So, we could write the rate of disappearance of the substrate, which we will see in a minute, equals the rate of formation of the product. So, this is the rate of formation of the complex ES given on the screen by equation 5, and another equation that we have is a constraint equation, which says that the total amount of enzyme, be it in the free form or the free form plus the form in the complex together, is a constant which equals what we started with, right. So, once we do that, then the rate of formation of product is dCp dt is K2 times CES. Now, a very important assumption that we make, which we test in the next few minutes, is a quasi steady state assumption that the rate of disappearance of the complex is 0, because it is a short lived intermediate. The rate of accumulation of the complex rather is 0, because it is a short lived intermediate compound. Now, once we make that assumption, what turns out is that the equation 7, that is the rate of formation of the product, is negative of the rate of disappearance of the substrate, right. Okay. So, this is all fine. Then we do a little bit of algebraic manipulation, let us forget all of that, and we get rid of CES, the complex, some concentration of the complex, and we get rid of CE, the concentration of the enzyme. Why do we do that? Because these are not measurable quantities. We want a solution in terms of measurable quantities, which is the concentration of the substrate and the initial concentration of the enzyme. Clear? So then we go through these calculations. Let's forget all these calculations, and then we come up with the reaction rate, which is given by equation 12. Now we don't know if this reaction rate resembles the Michealis-Menten form. So what we do is we simply compare it with the Michealis-Menten form and figure out, yes, it does look like the Michealis-Menten form, and then we convert it into Michealis-Menten form. The reason we do that is we can come down from 4 parameters, which are hard to measure, to 2 parameters, which are easier to measure experimentally, and then we go ahead and measure it experimentally. We talked about 4 different ways of measuring it. One is asymptotic analysis, the second one is a linear curve where you take the inverse of that and it's easier to measure, and then there's a scattered plot and the Eadie-Hofstee equation, and the final thing we tested is the quasi steady state assumption, whether that is valid or not. And what we figured out is that it's not necessarily valid under all conditions, and the way we did it, we split the entire reaction, the 2 reactions that happen, into 2 parts. So the first reaction is supposed to be fast, and the second reaction is supposed to be slower, and during the first reaction which happens, we assume that the concentration of the substrate equals the initial concentration, and taking that and taking an initial condition that there is no complex present, we integrated that, we found a dynamic solution to that, and we use that to get to the second part. And then we compared the rate constants of the first part and the second part, and we figured out that if the second part is much slower than the first part, then only it is possible to assume a quasi steady state relationship, and then only can we get to a Michealis-Menten form, right? So and that was and so what we figured is that, yes, if there is this is possible if a certain relationship between the initial enzyme concentration and the initial substrate concentration is maintained. So I guess we'll stop here today, and next week we'll continue with how to regulate these enzyme activities, okay, which is a different section. So thank you.